Hello everyone, this is Uday Kumar, working as Assistant Professor of Physics in Dr. B.R.R. Government College, Chella. So, as you already know, we are dealing the chapter Digital Electronics, and even today we try to understand the other topics of the chapter, which is Digital Electronics. Okay, so fine. So these are the topics that we are going to deal today. Okay, so in today's video we try to understand what is a Nand gate and what is a NOR gate, and what are the universal logic gates and why do we call them. So these are the things that we are going to deal in today's video. So now fine, so let us move on to the first topic of today's video lesson, which is a NAND gate. Okay, so now we try to understand what is a NAND gate and how do we represent the logical circuit diagram, okay, logical symbol, and then next we also try to understand the truth table and the all the details that are regarding the NAND gate that we try to understand in this slide. Okay, so fine. So what is a NAND gate? So in simple words, you just try to remember that it is the combination of and NOT gates. So you know what is an AND gate, and you also know what is a NOT gate. So this NAND gate is the combination of and NOT gate. Okay, so fine. And then the next one, so the output, so that means it is the definition of NAND gate. The output is high when either or both the inputs A or B is low. Okay, so this is the definition of NAND gate. So this definition you can understand from the truth table that will come after a few steps within this slide. So this definition I will come to it once again once we understand the truth table. And similarly, this is also the other definition of NAND gate. So the NAND gate can be defined by this one, which is the output is high when either or both of the inputs A or B is low. And this NAND gate is also defined as the gate in which the output is normally high and going low only when both A and B are high. So this is the another definition of a NAND gate. So you can write any definition that you want, but to understand these two definitions, two statements, you need to know the truth table of NAND gate that we try to understand. Anyway, coming to the first step, so this is the first step that we already know, which is the combination of and NOT gate. So you know that just now we have studied that NAND gate is the combination of and NOT gates. Okay, so you know what is an AND gate, right? So this is an AND gate. So this is an AND gate. So you know this one, and we already studied what is an AND gate. So this AND gate will have two input terminals and one output terminal, right? So that means it has two inputs and one output. So the inputs are denoted by A and B. Okay, you can denote the inputs by any symbols that you want, but I am taking here them as A and B. And you know that if A and B are the inputs of the AND gate, the output I can write this as C is equal to A dot B, where this dot is nothing but the multiplication which is the logical function of the AND gate, and A dot B we call it as the logical equation of the AND gate. Okay, so anyway, so here A and B are the inputs of the AND gate, and C, which I can write it as A dot B. Okay, this becomes the output of AND gate. So this is an AND gate that we already studied, and you know the truth table of this AND gate also. What is the truth table? The operation of this AND gate can be understood with the help of a truth table, which we call it as truth table. Okay, so that's it. So remember, the operation of this AND gate can be understood with the help of a table, which we call it as truth table. So now the truth table of this AND gate is already known to us. So this is the truth table of AND gate. Forget about this column. Okay, so this is not necessary to you. So the AND gate, so that means the entire AND gate can be understood with the help of these three columns. Okay, So where A and B are the input terminals of AND gate and C is the output of AND gate, which I can write it as C is equal to A dot B. Okay, so now you already know that the potentials or voltages that can be given to both inputs can be either low or high, right? So the possible combinations of the voltages that can be applied to the inputs can be written as 0 0 and 0 1, 1 0 and 1 1. So you know these things, right? So that means I can apply higher potential or lower potentials to both A and B, and the possible combinations can be 0 and 0. 0 means it shows that it is low potential, and 1 shows that we are applying high potential. Okay, so now 0 and 0 means if you apply low potentials to both A and B, we get the output as 0, and 0 and 1 means we are applying low potentials to A and we are applying high potentials to B. So if I apply this condition of 0 and 1, again the output will be 0, and if I apply high potential to A and low potential to B, then also the output C will be 0, and if I apply high potential to both A and B, then only the output of the AND gate will be high, which is symbolized by 1, which is denoted by 1. Okay, so this is the truth table of AND gate. So that means this truth table will help us to understand the operation of working of this AND gate. So I hope it is clear. So this we already studied, but here in this slide we are studying NAND gate. So what is NAND gate? So NAND gate is the combination of AND and NOT gate. So till now we just studied what is an AND gate. We just revised what we already have studied. So this is an AND gate and it is the truth table of AND gate. But NAND gate is the combination of AND and NOT. So that means if I apply this output of the AND gate to a NOT gate, you will get the NAND gate. Okay, so I hope it is clear. So this is and this is NOT. So that means the NAND gate is the combination of AND NOT gate. Is that clear? So that I hope it is clear to you. So this is AND gate, this is AND gate, and this is NOT gate. Okay, so the combination of AND plus NOT gives you NAND gate. So this is what you have to understand. This is NAND gate. Okay, so anyway, you know what is and you also know what is NOT. What is a NOT gate? It is an inverter. Okay, it is an inverting gate. That means whatever the input that you apply, the output will be the inverse of the input. So that means here C is the output of the AND gate, so that you can understand from the figure, but this C will be the input of NOT gate also. Is that clear? Here C is the output of AND gate and C also will be the input of NOT gate. So since the input of NOT gate is C, here the output will be C bar, so that you have to understand here. So here we are applying C to the input of NOT gate, right? So that means the output must be C bar. So this C bar you can take in any way. So you can take it as X, you can take it as Y, you can take it as Z, whatever it may be. Okay, here I have taken it as X now. So here X is the output of NOT gate, and this is nothing but the output of NAND gate also. You can say that here X is the output of NOT gate here from the figure, and it is also the output of the entire NAND gate. So that you have to understand here. So I hope it is clear. So please remember, this C is the output of AND gate and also it is the input of NOT gate, and hence I can write the output of the NOT gate or NAND gate here as, you can take it as X, Y, Z, whatever it may be. Here I have taken it as X, so now X becomes C bar because C is the input of the NOT gate here. Okay, so please try to get is NOT gate is an inverting gate, so whatever the input that you apply, the output will be the complement of input. Okay, so here C is the input of NOT gate and hence the output will be C bar. So that is what you have to understand, but you know that C is nothing but A dot B. So in place of A dot B, if I substitute, what do I get? I get x as a dot b bar also. So you can write x as c bar or a dot b bar. So choice is yours. So anyway, so this is combination of and not gate, which gives you a NAND gate. So anyway, so you understood the truth table of AND gate. So now we try to understand the truth table of NAND gate also. So what is the output of NAND gate now? So this x gives you the output of NAND gate. But what is x? X is nothing but a dot b bar, right? So here we have found a dot b. So if you find its complement here, if you find its inverse here, which you can see here, sorry, this is not C, it's by mistake, I must have written it. So this is not C, this is actually taken as X, right? So this is not C, this is X. Okay, it's a typing mistake, please rectify it. So this is taken as X here. So since I have taken it as X, so this X I can write it as a dot b bar. So now I know the values of C, I know the that means the voltage values that you get at the output of the AND gate, that we have found based on the different combinations of inputs. But now I want to find the output of NAND gate. To find the output of NAND gate, what do I have here? I have a dot b. Just substitute a dot, that means just find a dot b bar. So whatever the values that you get here, so just write the inverse values here, so you automatically get the output of NAND gate. Okay, so I hope it is clear. So that means I have 0 here. Since I have 0, what will be the value of a dot b bar? This is a dot b, so please check it out. This is a dot b, and what is this? This is nothing but a dot b bar. So a dot b bar means 0 becomes its inverse. What is its inverse? 1, and this 0 also becomes 1, and this 0 also becomes 1, and this 1 becomes 0. So whatever the values that you get here in the fourth column, so this is taken as first column, second column, third column, and this is fourth column, right? So whatever the values that we have in fourth column, so this is the output of AND gate, but this is which I have written in fifth column, this is the output of NAND gate, so that you try to understand. Anyway, so that you can even see here I am erasing everything. Okay, so this one, so this is A and B, which are the inputs of the NAND gate. Of course these are inputs of AND gate also, but in overall if you compare these two, A and B becomes the inputs of NAND gate now, and this x is equal to c bar, which is also written as a dot b bar, becomes the output of NAND gate. So here A, B are the inputs of NAND gate, and this c is equal to a dot b bar becomes the output of NAND gate. So you can forget about this. You can forget about this. Okay. So because this is the output of AND gate that you get here in between. Is that clear? So this C is the output of AND gate and also input of NOT gate, but the inputs of the NAND gate becomes A and B, and the output of NAND gate becomes x is equal to c bar, which I also can write as a dot b bar. So now every time you cannot draw AND plus NOT in place of NAND gate, right? So the simplified logical symbol of a NAND gate is given by this diagram. Okay, so remember this is AND and this is NOT. So remember the AND is drawn here and the NOT is having a circle here. Is that right? Can you see that? That circle is drawn over here, that's it. Okay, if you draw a circle here, so this combination becomes NAND gate. So please check it out. This symbol from here to here is nothing but AND gate, and this circle shows that it is the combination of AND and NOT. Okay, so I hope it is clear. So remember, once again I just revise it quickly. So NAND gate is the combination of AND gate and NOT gate, and in simplified, so by combining them I can draw the NAND gate by this one. So if the inputs are A and B, and the output of NAND gate will be A dot B bar. Okay, so that you try to get it. Remember, the output of the AND gate will be A dot B, but the output of NAND gate will be A dot B bar. So that you have to understand, that is the difference between AND gate and NAND gate. Okay, so AND gate's output is written as A dot B, but the output of NAND gate is written as A dot B bar. Okay, that you try to get it. Both are same here. These two diagrams are equivalent to each other. They are equal. But here we have drawn the circuit diagram separately as the combination of and not. But this is the simplified form. Okay. So here this shows the AND gate and this circle shows the NOT gate. So when you combine these two, you get NAND gate. So that is what you have to understand. So now from the truth table, you can define what is NAND gate. Okay, so now let us try to understand the definition of NAND gate. So how do I define NAND gate? So please have a look at it. You can forget this, that's what I am saying. Okay, so this is the output of AND gate. This is the output of AND gate. But what are we studying here in this slide? We are studying the output of, it's in simple words, we are studying NAND gate, not AND gate. So now if now A and B becomes the inputs of NAND gate, and C, okay, in place of C you can write it as X here, not C, you can take it as X. It's a printing mistake, please check it. So now A and B are the inputs of NAND gate and X becomes the output of NAND gate. So when the inputs are 0 and 0, we are getting 1, and when inputs are 0 and 1, we are getting 1, and when the inputs are 1 and 0, we are getting 1. So that means out of 4 combinations, we are having three cases where we are getting 1 at the output, right? So that means in general, in other words, so this is the definition that we are studying now. First one, this is the third case that we are studying. So in general, it is normally high. Okay, are you getting me? Why we are saying that it is normally high? Because out of 4 combinations, 3 combinations we are getting as high. Okay, 1 means high voltage, right? So out of 4, we are getting the 3 cases where the output is high. So that means we say that the NAND gate is a gate whose output is normally high. But there is one case where the output is low, and that low condition is studied here, okay, mentioned here. So please check it out. It is normally high, the output, so that means NAND gate is the gate whose output is normally high and going low only when both A and B are high. So that means the output of NAND gate will be 0 at what condition? When both A and B are 1. So that condition is mentioned here as the definition of NAND gate in the third step. Okay, so this is the third step, right? So that means the NAND gate is defined as a gate whose output is normally high and going low only when both A and B are high. So this becomes one definition of NAND gate. So now coming to this definition. So the output is high when either or both of the inputs A or B is low. So can you understand? So now coming to these 3 cases. So the output of the NAND gate is high, right? When the output of NAND gate is high, that you try to observe here. So for the case of 0 and 0, output is high. For the case of 0 and 1, the output is high. And even for the case of 1 and 0, the output is high. That means if the inputs are having that means we have 2 inputs here, right? A and B. So if any one of the input or both the inputs, if their values are low, then automatically the output is high. So that step is mentioned as a definition here. So remember, so the output is high. So can you see? You just observe here. Here we are having high. Here also we are getting high. Here also we are getting high. But to get high values, what are the combinations of inputs that we have taken here? So the if you observe this first combination, we have A and B 0, but in second combination we have A as 0, and in third combination we have B as 0. That means any one of the input can be having 0, and if both the inputs are having 0, so this case shows that both the inputs are zeros, and these two cases shows that when any one of the input is 0. So if you combine these two conditions, we get a definition that is written in this step. So that means the output of, so that means NAND gate is a gate whose output is high when either or both of the inputs A or B is low. That means if any one of them can be 0, or if both of them can be 0. So if any one of the input is 0 and both the inputs are zeros, then automatically the output will be high. So that definition is written over here. So I hope this is also clear. So you just try to understand it once again. So the NAND gate is the gate whose output is high when either or both. So that means if any one or both the inputs are low. So please check it out. Low means 0. So that you have to understand. I hope this definition is also clear to you. So now, so this is the NAND gate. So now let us, this one is very important for your board examination, so please try to remember it one, this one, right? And the next one, let us just move on to our next slide, which is NOR gate. So what is a NOR gate here? So again, NOR gate is the combination of OR and NOT gate, okay? So it is the combination of OR and NOT gate, okay? So you already know what is an OR gate and what is a NOT gate. Okay, anyway, NOR gate is the gate whose output is low when either or both of the inputs A or B is high. So this is one definition of NOR gate. And coming to the another definition, so in other words, this is another definition of NOR gate. It is normally low and going high when only when both A and B are low. So this is the another definition of NOR gate. So to understand these two definitions, first of all, we need to understand the truth table of NOR gate. So anyway, as I already told you in the first step, it is the combination of OR and NOT gates. Okay. So remember one more point I just forgot to mention. So whether it is NAND gate or NOR gate, in general, we have two inputs and one output. So that you have to remember. So anyway. So now, as I already told you, this NOR gate is the combination of OR gate and NOT gate. So in our previous videos, we try to understand what is an OR gate and also NOT gate, right? So when you combine this OR with the NOT, you get a gate which we call it as NOR gate. So let us try to understand NOR gate in terms of the combinations of OR and NOT. So you know what is an OR gate, right? So this is OR gate. So the circuit symbol of the OR gate is denoted by this one. So you know that OR gate is a logic gate which is having two inputs and one output. And if I take the input terminals as A and B, the output of this OR gate I can write it as C is equal to A plus B. So that you have to understand here. So in earlier case, we have combined AND and NOT gate to get NAND gate, right? Similarly here we combine OR and NOT gate. So when you combine OR and NOT, first of all you have to understand what is an OR gate, which we already studied. So OR gate is a logical gate which is having two inputs and one output. If I take the input terminals as A and B, and the output becomes A plus B, which I can take it as C. Okay, so where this plus is called as the logical function of OR gate, and A plus B is called as the logical equation of OR gate. So you know this is OR gate, and you also know the truth table of OR gate, right? So what is the truth table of OR gate? So truth table of OR gate is nothing but a table which explains the operation of this entire OR gate. Okay, so now coming to the truth table of OR gate, you already know this truth table of OR gate. So this is an OR gate whose input terminals are A and B. So we have input terminals as A and B, and the output of this OR gate is taken as C is equal to A plus B. And forget about this column now. just for some time. Forget about this. We are studying only OR gate now. Okay, so now we can, as you already know, we can apply either high potential or low potential to the inputs, and even the output will be either high and low potential. So this high and low potentials can be denoted by 1 and 0 respectively. That means if you apply low potential, it is denoted by 0, and if you apply high potential, it is denoted by 1. So anyway, you can apply low and high potentials to both input terminals, and the possible combinations will be 0 0, as you already know, 0 0, 0 1, 1 0, and 1 1. So that means if I apply 0 potential to both A and B, then there is, okay, so I have applied 0 potential to A and also B. So if I apply 0 potential to both A and B, the output of the OR gate will be 0, you know this one. Similarly, if I apply 0 potential to A and high potential to B, the output will be high, which is denoted by 1. Similarly, if I apply high potential to A and 0 potential to B, the output will be again high. Okay, and similarly, if I apply high potential to both A and B, even at this case, the output will be high. So that means 0 plus 0 is 0, and 0 plus 1 is 1, and 1 plus 0 is 1, and 1 plus 1 is also 1. So this is the truth table of NOR gate. So that you have to, this is the truth table of OR gate. Okay, OR gate. So that you have to understand. But we are not studying the OR gate here. We are studying the NOR gate, which is the combination of OR and NOT. Okay, so now you know what is OR, and if I combine this OR to a NOT gate, so this entire or the combination of this OR and NOT gate is called as NOR gate. So that you try to understand. So now this C becomes the joint to both OR and NOT gate. Okay, so it's a common thing now. So C becomes the output of OR gate. Okay, and this C also becomes the input of NOT gate. So that you have to understand here. So if a C is sorry, I just that means I just made a small mistake here. I think I said C is output of OR gate, which is right, and this C also becomes the input of NOT gate, input. So I hope that is what I said. Here C is the output of OR gate, and C also becomes the input of NOT gate. Okay, so that you try to understand here. So if C is the input of NOT gate, so now the output of NOT gate becomes C bar. Okay, so that you have to understand, because it is an inverting gate, right? So whatever the value that you apply at the input, the output will be its inverse, its complement. So since I have taken the input of the NOT gate here as C, we get the output by C bar. Okay, we mention its output by C bar, but you know that C is equal to A plus B, right? So I can write its output by A plus B bar also. That means this C bar or A plus B bar, I can mention it with some other symbol, and that other symbol I have taken here by X. Okay, so that you try to get it. Remember, here C is the output of OR gate and input of NOT gate, but here C bar or A plus B bar becomes the output of NOT gate. So in other words, if I forget this C here in between, A and B becomes the inputs of NOR gate, and X becomes the output of NOR gate now. So that you try to understand. Anyway, the truth table of OR gate is known to us now. So I am erasing everything now. Just erase everything. So now you know what is C here. We have different values of C that we got in this table. So here, but the output of this NOT gate or NOR gate is not just C, it is C bar. C bar means this is also can be written as A plus B bar. So here whatever the values that you have here, coming to this column, we get its inverse values. For example, here I have 0 here, right? So which is A plus B. But and remember again, I have wrongly typed here. So here there should not be x, sorry, there should not be c, we should have x here. So this is c, and here this is c bar, right, and hence this I can write it as x. Okay, wrongly typed, so please check this one. So this is c, which is equal to a plus b, and I know these values, right? So if c is 0, this is what, a plus b bar, that means a plus b bar will be 1, and if c is 1, here a plus b bar, c is nothing but a plus b. If a plus b is 1, a plus b bar will be 0, you know this one. Again here a plus b is found to be 1, and a plus b bar will be 0, and again if a plus b bar is 1, again at this case again you get 0. So this becomes a plus b bar, which is the output of the NOR gate. So this is NOR gate, output of NOR gate. This is output of NOR gate. Forget about this step. It is coming in between the combination of R and NOR. Again, this A and B becomes the inputs of NOR gate. So that's it. Inputs of NOR gate. Okay. So I hope it is clear. So now this truth table shows the operation or working of this entire NOR gate. So for convenience, let me erase everything. So here we have the values of C, which is the output of R gate. Okay. So now to get A plus B bar, okay, the values we get like this one, 1,000. So this is the column which shows the output of NOR gate, and these two are the things which shows the inputs of the NOR gate, and you can forget about this column. Okay, in your examination you can write this column or you need not write, so choice is yours. If you think that you may get confused, in such cases you write this column, otherwise you can only write this column, this one, and this one. That's it. Okay, so you need not write this one. If you want to write, you can write, but otherwise not necessary. So now based on this truth table, we can try to define, we can try to understand the definition of a NOR gate. Okay, anyway, so this is NOR gate, right? So which is the combination of R and NOR gate, and in simple diagram I can draw the logical symbol of NOR gate by this one. Okay, so this is R gate, and this NOT is represented by this circle here. Okay, so can you see this circle? So this NOT R circle shows that there is a NOT gate here, so that you try to get it. So R plus NOT, so remember this is R gate, and NOT is ending with a circle here. Okay, when you combine them, so this is what we get, and this we call it as NOR gate. And remember, so I have drawn some boxes here at A, B and X, right? So you may draw these boxes or you need not. I just drawn them to show that there are certain terminals. So that means these two and this one, these three boxes shows that there is a terminal to connect something. Okay, and those terminals are nothing but A, B and here X. So only to mention them, I have drawn them with boxes. If you don't want to draw, you can draw this NOR gate like this also. You need not draw any boxes at A and B. So this is an NOR gate, and this is the NOR gate, and this is the output. Even you can draw in this way also. So this becomes NOR gate. Okay, OR gate means there will not be any circle here. That's it. That's it. Anyway, so this is NOR gate. I hope it is clear to you. Okay, so now based on this truth table, you can write the definition of NOR gate. So what is NOR gate? So now come to the first definition. The output is low when either or both of the inputs A or B is high. So this is the definition. Okay, so the output is low. So out of these four combinations, Okay, if you observe carefully, out of these four possible outputs for different combinations of inputs that we are getting, if you observe these four cases, out of four we are getting three cases to be zero, right? Low. Zero means low. So that means in general the output is low except at one case. So in general the output is low. Okay, so that output condition you are getting when a is 0. Okay, um, okay, so here 0 is not common in all the three cases. The common thing in all the three cases is 1. So please check it out. In second case we are having 0 and 1, right? So that means 1 is there. Even in third case we are having 1 and 0, which is again 1 is common. And in fourth case also we are having 1 at both A and B, right? So 1 is common in all these three cases. So based on that common point we can write the definition. So that means if any one of the input or both the inputs are high, then the output is low. Is that clear? If any one of the input or both the inputs are high, then the output is low. So that definition is written over here. So please check it out. The output is low when either or both, that means any one of the input or both the inputs are high. So that's what you have to understand, right? So please check it out. Here we have 1. So that means if I have 1 at B, you are getting 0. And if I have 1 at A, then also you are getting 0. If I have 1 at A and B, then also you are getting 0. That means the NOR gate is the gate whose output is low when any one of the input or both the inputs are high. So that is the definition that is mentioned here. So this is NOR gate. Again, there is one more definition that you can write here. And what is that definition? In other words, it is normally low. So as I just told you, just a few minutes back, I told you that out of 4 cases, in 3 cases you are getting 0, right? So that means in generally the output is low. Only in one case the output is high. And at which condition we are getting the output as high? When both A and B are zeros, then we are getting the output as high, right? So that definition is mentioned in this step. So in other words, the output of NOR gate is normally low and going high. Okay, at what condition the output is high? When both the inputs are zeros. 0 means low. So that definition is written here. So in other words, it is normally low. Okay, so that means NOR gate is a gate whose output is normally low. Normally low means out of 4 cases we are getting in 3 cases the output is 0, right? So that condition is mentioned here. So in other words, the NOR gate is a gate whose output is normally low and going high only when both A and B are low. So that you have to understand here. So only in one condition the output is high. And what is that condition? When both the inputs are low. So that condition is mentioned here. So this is the NOR gate. I hope it is also clear. So remember, NAND gate and NOR gate is also an important concept to your board examinations or competitive examinations. Remember, these NAND and NOR gates are called as the derived gates. Okay, so that means the basic gates are OR and NOT gate, right? So that means we have 3 basic gates: OR, and NOT gate. Okay, so if you combine OR and NOT, you get NOR gate, and if you combine and NOT, you get NOR gate. So now these NAND and NOR gates are called as universal logic gates. So this is what you have to understand. So which is very important question to your board examination. What is this? This is universal logic gates. Okay, so NAND and NOR gates are called as universal logic gates. Just now we have studied what is a NAND gate and what is a NOR gate. So this NAND and NOR, these two gates are called as universal logic gates. So why do we call these NAND and NOR gates as universal logic gates? The answer lies here itself. Because we can construct basic gates like OR and NOT gates by using NAND and NOR gates only. So that means by taking NAND gates only, you can construct OR gate, you can construct AND gate, you can also construct NOT gate, and hence NAND gate is called as a universal logic gate. Similarly, even by taking NOR gates only, you know what is NOR gate, right? So by taking NOR gates only, you can construct OR and NOT gates, and hence NOR gate is also called as a universal logic gate. So remember, NAND and NOR gates are called as universal logic gates because we can use these NAND and NOR gates to construct the basic gates. So what are basic gates? OR and NOT gates. That's it. So since NAND and NOR can be used to construct the basic gates, we call this NAND and NOR gates as universal logic gates. Okay. So anyway, because of time factor, I just stop here. In our next video, we try to know how the NAND gates are used to construct. Can you see this heading here? So we can use NAND gate to construct a NOT gate, and you can use NAND gates to construct OR gate, and you also can use NAND gate to construct AND gate. So how do we take NAND gates to construct OR and NOT gate? All those things we try to understand in our next video. Similarly, in our coming videos, we also know how do we use NOR gates to construct OR and NOT gate. Okay. So we discuss about these universal logic gates in our next video. Until then, okay, goodbye. So thank you. We will meet again. Thank you once again.